Hello everybody and welcome to the video manual for the MRB Zeroscillator. Wow, the Zeroscillator looks pretty complicated. There's lots of stuff on here, but it's actually pretty easy once you know what everything is. And we're going to go on a detailed tour, but for now let me just talk about the fact that we've got exponential FM inputs over here, we've got linear FM inputs and their controls over here, we've got quadrature outputs up here, we've got waveform morphing, we've got all the various outputs here, and we've got the mysterious time reversal jack down here. Now, does that mean that the Zeroscillator can actually take you backwards in time? Well, in a word, yes. And in order to explain all that in a way that even I can understand it, I'm going to invoke something called the wheel analogy. And for that, we're going to need a wheel. Oh good, here's one. And it's got a pretty yellow dot on it. Now if we follow this yellow dot around the wheel and pay attention to its vertical position, it traces up and down. And if we plot that up and down motion over time, we get what? Anybody? Anybody? That's right, a sine wave. But what if this wheel is going in the opposite direction? The yellow dot still goes up and down. What waveform does it trace out? You guessed it, also a sine wave. Now let's go over to the Zeroscillator and see what it does when we put positive and negative control voltages into the linear FM input. It's just like the wheel going clockwise for positive voltage and going counterclockwise for negative voltage. Do these two sine waves sound any different? Let's see. Okay, so here we are back with the Zeroscillator, and I've got an oscilloscope hooked up. We're looking at the sine wave, and I've got the DC source dialed in at 5 volts going into the linear FM input. And what does this sine wave sound like? Sounds like a sine wave. Well, what happens if I edit this voltage, and instead of 5 volts, I make it negative 5 volts? Well, look at that, it's a sine wave. And what does it sound like? Sounds like the identical sine wave, so what's the purpose of all of this? Why do I bother with the positive and the negative? Well, we're going to see what happens back at the wheel. Starting with a positive control voltage, the wheel will spin clockwise. When the control voltage passes through 0, the wheel will slow down, stop, and reverse. And every 0 crossing of the control voltage, the wheel will change direction. Notice that it stops and reverses wherever it happens to be. Right now, the control voltage stopped at 0 and the wheel, or the oscillator, has stopped entirely. Well, what kind of output does that make? Well, we'll look at the Zeroscillator and the oscilloscope and find out. Okay, well, let's see that wheel go forward, wheel go backward action with the Zeroscillator. Let's turn it up a little. And wheel go forward. Wheel slow down. Stop. We'll go backwards. We'll go forward. How fun. But how do we know that it actually went forward and went backward? The sine wave looks like a sine wave. All right, well, let's check out some other waveforms. Here's the triangle wave. Forward, backward, forward, backward. Still looks like a triangle wave. Let's sync it up here. Forward, backward, forward, backward. Still a triangle wave. How about the square wave? Forward, backward, forward, backward. Still looks like a square wave. Well, how can we tell it's going backwards? How about the sawtooth? The sawtooth has directionality to it. Sometimes one is called a saw and the other is called a ramp, or a saw and an inverse saw. Anyway, ramp go up, ramp go down. Maybe the sawtooth will reveal to us what's really happening. So we go to the sawtooth. Here we go. Saw go up and then stop. Look at that. Saw go down. It's actually reversing in time. Remember what I said about the Zeroscillator taking you backwards in time? Backwards in time, forwards in time. That's really what's going on. A lot of explanations out there have claimed that through 0 FM is just, well, when the control voltage goes through 0, the waveform inverts, or some other crazy explanation. That's not what happens. What happens is the oscillator stops when it goes through 0, and then it runs backwards. It legitimately runs backwards. In the hardware version of the Zeroscillator that I designed back in 2005, there's actually a whole bunch of circuitry in there that makes sure that this actually happens. There's a voltage comparator in there, and when it senses the linear control voltage has gone through 0 and it's gone negative, it activates a whole bunch of high-speed analog switches that actually rewires the circuitry of the oscillator so that it runs the other way. I can't stress this enough. Anyway, that's what through 0 FM is. We've gone all this way to really give you an intuitive understanding of what it means to go through 0 in a through 0 oscillator. I hope I've made my point. So, even though it's a whole lot of fun to go back and forth like this with the knob, that's not too practical. So we're going to disconnect the DC source, and I'm going to connect up an LFO to do the same thing. And we're going to try to catch one of these reversals in action. See if we can do it. Okay, there's a reversal. You can see that the frequency goes down, it gets very low, and right at this instant, the control voltage went through 0, and it reverses. It looks just like you put a mirror right here and reflected the left half into the right half. And so you can see a time-reversed version of what's on the left appearing on the right. It's these reversals that give FM synthesis its unique timbre. All right, enough with FM 101. Let's get into making some noises. I've got the Zeroscillator up here with an envelope generator and a VCA, so we don't have to hear the oscillator squawking all the time. Just hit a note, and we can hear it. And let's see, I've got the triangle wave on display, and we're also listening to it. I like listening to the triangle wave other than the sine wave. It's easier to hear really what's going on because there's more harmonics in it. And I've got some DC going into the linear FM input, so the oscillator will run. So if I play a scale, we can hear it. Now I'll just hold down a note. Now you can hear that every time the DC goes through 0, no matter what note I'm playing, it's gonna take me through 0. So we always need some DC going into the linear FM input for the oscillator to run. So instead of having to patch this up all the time to provide some bias, right over here is the bias. So I'll disconnect it. Right now the bias is 0. We only hear thump, thump, thump because the oscillator has just been stopped right there. And if I turn on some bias, here's low bias. We can hear something. Now I'm just going to hold down one note and move the bias around. No change. How come? Well, in the hardware version of the Zeroscillator, there was a change, but I added this little feature that as you change the bias, just like moving this control up and down, it compensates for that and keeps you at the same tone. So that means as you change bias, you don't have to retune to get back where you were. So that's kind of convenient. So with the bias in place, we can get to the primary function of the Zeroscillator. Okay, so I've gotten rid of the DC module, and in place of that I have an oscillator. I've got the sine wave going in. We're also listening to the sine wave this time because that's what FM usually does. Most FM patches are going to be listening to the sine wave. And if we listen to this sine wave and this sine wave, you can hear that they're both equal in frequency. We have both oscillators tuned to the same frequency. So I play a note. Notice also I have the bias turned up all the way. And I dial in some modulation, linear modulation. Usually an envelope is going to do this, and we'll show you how that works in a moment, but I'm just doing it manually. To illustrate a point, I'm going to turn down the bias one notch. Try it again. A little more intense. Down another notch. Even more intense. Now down to the minimum amount. Now, why does lower bias give you more intense modulation? Well, we're going to see right now. Okay, so here's a graph that should make everything abundantly clear. I've got two lines graphed here, two different formulas. The red line represents the exponential control. 2 to the x. Every time x goes up by 1, we get a doubling. So at 0 volts, we're at 100 hertz, let's say. At 1 volt, 200, 2 volts, 400, 800, and 4 volts, we're up here at 1600. If we go negative, at -1, we go from 100 to 50, then to 25, 12.5, 6, 3. And as you can see, it never goes through 0. No matter how negative we get with the exponential control voltage, it won't go through 0. It just gets slower and slower and slower. We could go to negative 100 billion volts, and we still won't go through 0, but it will be very slow. On the other hand, the linear control voltage is happy to go through 0. And we're right here at 100 hertz per volt. So at 1 volt, we're at 100. At 2 volts, we're at 200, 300, 400, 500. And then at 0, we're at 0, where the oscillator stops. Then we're into negative frequencies. Up here, oscillator goes this way. Down here, negative frequencies. You might have heard that term. The oscillator goes the other way. So what about this bias? We have no bias here. At 0, we're at 0. So let's add some bias and see what happens. I've added 200 hertz of bias. So now at 0 volts on the modulation, on the linear modulation, we're still running. And we have to go down to -2 before we'll go through 0. This represents 100% of the range. So 200 hertz is 100% of the range. And then if we go up to +2, we're at 400. So this is plus 100% and minus 100% before we get to 0, before it starts reflecting and going into negative frequencies. So if we modulate with plus and minus 2 volts, you can see that we never go through 0 from here to here. But what if we have less bias? What if we lower it? What if we lower it to 100 hertz? Now you can see, to make it into the negative frequencies, we only have to move a volt. So 2 volts of modulation looks like more. And if we go even lower, let's say down to 50 hertz of bias, we only have to move a half a volt from here to here before we go through 0. So this represents 100% modulation. So you can see as the bias goes down and down, the value that represents 100% gets tinier and tinier. So when we put in modulation signals, big modulation signals, we get a huge range in the percentage of modulation, and that's why it sounds gnarlier. The modulation sounds gnarlier with lower bias. Okay, congratulations for sticking with me this far. I'm glad you all were able to take the brain boost on FM and basic Zeroscillator theory. So now we're going to get into actually hooking stuff up and making some sounds. So let's go on a little tour of some of the controls. A lot of the controls will be familiar to you. The tuning control is the coarse tune, and this is the fine tune. And a feature borrowed from my laboratory VCO is the quantized switch here. I'll demonstrate that. Hold down a note. We have a basic patch, sine wave, envelope generator, VCA, and we're listening to that. So when I hit a note, turn the coarse tuning, the usual result. Turn on the quant switch, and the knob will quantize to discrete semitones like this. makes things much easier to tune. And tuning is critical. Frequency ratios are critical, so being able to tune exactly to notes is an advantage. We went over the bias control, the range control, typical octaves, range control. And on this side we have the exponential modulation. And the 1 volt per octave is going to the pitch. You'll notice a 1 here. That means unity. The rest of these controls have a 0, which means when you have none, when it's at 0, you have none. But when you're at 1, that means you have 100%, and that means 100% keyboard tracking. If I turn it down, that was a scale, but it's no longer an octave. It's a half an octave when you play an octave on the keyboard, and you can also expand it. So you can mess around with different scales. They'll all be equal tempered, of course, but they'll be different scales. So different waveforms. We've got sine wave, triangle, square. Down here is the pulse width modulation. You can plug an LFO into the PWM control. Usual pulse width modulation. So if you're familiar with any VCO in the world, you're familiar with all of this already. To do basic FM, and I've got a basic FM patch here, you're going to need another VCO to be the modulator. The carrier, being the Zeroscillator, is the oscillator you're going to be listening to, and the modulator is the one that's going to be providing the FM. These two inputs, the modulator and FM index, form a VCA, where the modulator goes in here, and an envelope or some other control source, usually an envelope, goes into the FM index, as it's traditionally called, and modulates the amplitude of the modulator. It's as if you had a VCA out here. The linear FM input that we were using before goes directly into the core, so you can also provide that. So the modulator, together with the FM index, together with the linear FM, all sum together to form the linear modulation signal. And you'll find that linear modulation signal appearing here at the mod out. So you can use this to modulate something else, maybe another Zeroscillator or anything else you want. So that sounds like this. We have just the sine wave here. And we'll match the frequencies. And I'll turn up the FM index. And according to this envelope, we'll get FM. And the depth is controlled here. And as we learned, the bias also controls how much depth you get. Now, these two LEDs show you when you go from positive to negative frequencies, when you cross through 0. Turn down the index a little bit, keeping it on high bias, and that will keep us out of the negative world. If I turn down the bias, that makes it easier to get there, as we saw on the graph. And now we get into negative. We can show that even easier here. Let's get rid of this. We'll go directly into the core through the linear FM. Not getting there yet. And there, we're just starting to get there. Now, if I turn down the bias, you'll see we'll get there even easier. You can even hear it happening. So that's what the LEDs are all about. Now, due to the nature of the update rate of LEDs in Voltage Modular, you won't see a perfect rendition of what's happening on these LEDs, but they're there anyway. On the polyphonic version, since there could be up to 16 voices, I just left the LEDs off because there's really no point in showing anything, because it's just not going to make any sense. Now, in FM, the frequency ratio between the carrier and the modulator is everything. That's what gives you all the timbres. and of course the modulation depth, but it's really mostly the frequency ratio. So let's see what happens when we just change octaves here. Let's hear a difference in the character. Let's go up a fifth. Now here's an example of where we would use this control, the initial index. You can hear when I let go of the key, this envelope releases pretty quickly. This one hangs out for a while, so we hear what happens when this envelope drops. We can just hear a sine wave hanging out. And that doesn't sound like a bell sound that we had anymore. So what this initial index allows you to do is dial in some background FM and retain some character during those decays. Once again, without and with. Now, detuning also does a lot, gives some character. That's basically it. That's basically FM. So messing around with the different outputs, messing around with different input waveforms, different envelope shapes, that's really all there is to the FM part of the Zeroscillator. Now this switch here, this through zero typical switch, is just there to demonstrate, it was on the original hardware Zeroscillator as well. It just demonstrates what it would sound like if you had a typical oscillator and it doesn't have the ability to go through zero, and it would sound like this. So very, very different. That's why through zero is so great. Now here's an interesting thing. What if we don't use a sine wave as the modulator? What if we move over to the square wave? And we change the pulse width. What do you think's going to happen? Here's a hint. When the square wave goes positive, we move up to a certain frequency. And when the square wave goes negative, we move down to a certain frequency, and because it's linear modulation, they're equidistant from each other. So if we spend an equal amount of time up and an equal amount of time down, it sounds like this. But if we don't, pretty interesting, huh? That was kind of a surprise to me. Okay, let's add a little vibrato, and we would do that in the exponential side of things. And we'll use this LFO to do it. Adds a lot of character. All right, now we're going to get into the quadrature waveform morphing. And we're going to get into some stereo as a result. So we're going to have to change the patch a bit to make it stereo. Now here's a little demonstration of the wave morphing section. We're looking at this output right here. When the knob is all the way over to the triangle, it looks like a triangle. It sounds like a triangle. And turning the knob towards a sine wave, it will slowly morph into a sine wave, and you'll hear the harmonics disappear completely. Right there, no harmonics, really good pure sine wave. And as we move farther, it starts to morph into and turns into a square wave. Now, this is a true morph. It is not a cross pan between waveforms. As you can see, and the morph is voltage controllable. Let's say we set it right about here between sine and square. And we put an LFO in here. You get a nice waveform morph. I've got two VCAs in here now to listen to stereo. Let me look at the Patchcord so I see what I'm doing. And I'm going to hook up the other wave morph over here. This is how I get all these great stereo effects. Take that same LFO, but this time turn the attenuverter the other way. That is just gorgeous. I love the way that sounds. So the two sides are morphing opposite to each other. So let's look at some of the provided Zeroscillator presets and get into this in a little more depth and a little more sophistication. So here we are in the world of the polyphonic Zeroscillator and also the laboratory modules to support them, because I really think that they do a better job, and I'll show you why in a moment. So here's a bell patch. And it should be familiar to you now. So I've got the envelope generator controlling the index, the amount of modulation. The modulator is coming from this VCO. And I have the spread control turned on. And what that does is turns the fine-tuning knob into a spread knob. So this actually is controlling the detuning between the different voices, between the 8 different voices that we've got dialed in. So no two voices are modulating exactly the same, and that's creating a richness that you would not ordinarily get. And the same with providing the vibrato. I have the vibrato VCO turned down to LFO range and the spread control. So the sine waves that are coming out controlling the vibrato, which are also controlling the morph right now, are all different. They're all asynchronous, they're all out of phase, every voice is out of phase, and that's also controlling, also creating a lot of depth and richness. I also have the dynamic envelope turned up all the way, so if I hit a key lightly, I don't get much. Now, here's one of my favorite patches. It's called Slow Razor. It sounds like this. This is in the presets that you'll get to. And I just dialed it up so that you can hear for yourself how amazing this FM technique is. I'm just going to take the modulator down by octaves and the little X-ray into what's going on. It's amazing that that woo-woo-woo-woo, when sped up, actually gives you a timbre. You can hear the envelope taking it up and down. speed it up. Again. Again. So this is the same patch that we've been working with. It's using that opposite waveform morphing technique. I really like that one. Now, we haven't gone over the time reversal jack yet. And what the time reversal jack does, it's a logic sensitive signal. Whenever it's triggered, it reverses the sense of the FM. If the Zeroscillator thinks we should be in positive frequencies, it'll reverse it to negative. And if it's negative, it'll reverse it to positive every time it's triggered. So that's kind of like a sync, and we can use it as a sync. So what I've got going on right now is just an envelope controlling the pitch here on the exponential side. Like that. And if we run a signal into the time reversal, the modulator, instead of the carrier, usually the carrier defines the pitch. This time the modulator is going to define the pitch because it's going to be reversing this oscillator, and it sounds like this. Here's another little trick that's pretty much universal to Voltage Modular. Let's say I've got this turned up all the way, 100%, and I'm getting this much sweep. But I want more. What can I do? Well, I could put this through an amplifier or something, but there's an easier way. Remember, every jack in Voltage Modular is really multiple jacks, and those jacks represent a 6-way mixer. If I take the same signal and just put it in twice, I get twice the effect. If I take a third patchcord, put it in, I get 3 times the effect. So you can use that all over. Let's see what that sounds like with this. Completely different. Now, we haven't talked about the variable sync feature here yet. I've got 2 Zeroscillators modulating each other in kind of a Forbidden Planet sci-fi kind of sound. We'll just listen to this for a second, and then we'll turn up the Vari-Synch, and we'll hear what effect that has. Okay, going along nice and happy, and we'll turn up the variable sync. You can hear by changing the sync strength, it'll either lock on or have kind of a tenuous grip on things when you turn it down a bit. So it's a very different kind of sync sound than what you get with the time reversal. Of course, nothing stops you from using both at the same time. There are 7 different kinds of modulations that you can apply to the Zeroscillator to produce a wide gamut of sounds. And we certainly don't have time to go into all of it here. And I thank you very much for spending this nearly half hour with me on a tour of the Zeroscillator, and I hope that you have a good understanding of it and of all its controls. And I really look forward to hearing great music come out of each and every one of you using it. All right, so till next time, happy synthesizing.